Hello everyone, today I'll talk about the solution to the problem range sum of sorted subarray sums. Feel free to pause the video and read the statement if you're unfamiliar, and we'll go straight into the solution. Now, in this problem, it's classified as a medium, and the number of our numbers is up to 1000, so it allows us to get an n-squared solution, or even something slightly slower than n squared. This problem can be solved faster, but we'll stick at first to the n-squared solution, because it is allowed by the constraints. We're also being told that the answer can be a huge number, so we have to return it modulo, and it of course is necessary to return it modulo, but that number is not that very huge, and in fact in Python we in general don't have to care about it too much. Because of course Python has arbitrary precision arithmetic for any size of integers, though it becomes very slow if those integers become very large. Okay, so you want to essentially simulate getting a sum from left to right in the sorted array of all the subarray sums. We can just generate that array of subarray sums. So how do we do it in n-squared time? That's very simple. We can, for instance, iterate for every left end of a subarray that we're looking at, and generate all the sums of all the subarrays starting at that position. And in that case, we can utilize the fact that everything that we do is add a new element to the right. So essentially, if we have this original array, and we currently are looking at subarray starting here, then at first we have to add this element. Then we add this element to the sum, then this element to the sum. So at every step we generate one more subarray. There are quadratically many of those subarrays, by adding just a single element to the sum. And when we look at the next starting position, we just zero out the sum and add the first element, second element, third element, and so on. That's exactly what we do. The sum always starts at 0 for every start, and for end we add the value of that end and add the sum to our list, and of course then we sort this list. And this line 15 is the most demanding when it comes to running time complexity. So what would you say the running time is of this operation? Well, here's how we would go about finding it out. First of all, we have the size of our array. And if the size of that array is, let's say, s, then of course we can sort it in time s log s. And it's not possible to do it much faster than that. This, of course, is a big O complexity. And so, since in our case s is equal to n squared, we have n squared logarithm of n squared. Now, logarithm of n squared is what? Well, it's 2 times logarithm of n. So we get 2 times n squared logarithm of n. We get rid of the 2 in big O notation. So it's just O of n squared log n. Well, you can omit those parentheses or not, if you want. So this is the most demanding when it comes to time, and possibly also when it comes to space. And after that, we can just calculate the sum. We might just use a slice. It costs us the creation of that temporary slice, but it makes it succinct to express the rest of the algorithm. So we just take the sum on that slice. We take it modulo, as we're being asked to do. We only need to take modulo at the end because the numbers are small and there is a small number of those numbers. Because of course numbers are up to 100, there is 1000 of them, so a subarray sum is about the size of 1000 times 100, so it's not that big considering that there is only about 1 million of them. So you can sum them up all together and then just return it modulo at the end. If of course the numbers were bigger, then we would have to modulo going along the way to make sure that the numbers don't get very, very large. And when it comes to a faster solution than this, so that would be a solution that does not create and sort this array, just as we do here explicitly. And that requires us to figure out an algorithm that can operate on that hidden array and somehow determine exactly the result. So there are 2 standard tricks that we want. First of all, we want the sum at this hidden array from index left to index right. So that's the same as taking the sum to index right and subtracting the sum to index 1 to the left of index left. Right? The sum of this array. So let's say we have an array, we have this subarray, so we can just take the sum of this thing as a positive, subtract the sum of this thing, so the thing up to here, having this element that's before our subarray, and that is the same as the sum of the whole array. Also, what's useful, especially considering that all the numbers are positive. Now, all the numbers being positive is that it for instance, gives us that if we have a subarray, then all the subarrays of that subarrays have a smaller sum. All the super arrays of that subarray have bigger sums. And those two things together tell us that if we can use that property, that monotonic property, and if we can just calculate the first k sums in that array, we'll be able to calculate the final result. And indeed we can do so. We can do so using a binary search, and that binary search would be probably in every step, it will be looking at all the starts for all of our sliding windows. But in this case, it will not be quadratic, but linear, so we will just be starting at every position. And seeing how long we can make the subarray starting at this position, such that the sum of it remains smaller than some given number. So we will be binary searching a value of a sum and counting how many subarray sums are smaller than that value, how many are bigger than that value. Because if we reach the rightmost end of the subarray, where this subarray is still below this value, then we know that all the smaller subarrays starting at this position are also smaller than that value. But more importantly, if we were to push the right end forward, you would have all the subarrays starting at this position left that are bigger than the value. So you can go through all the subarrays in this sliding window fashion in linear time in a single operation, and you can count the number of subarrays that have sum greater or smaller than the given value. So you can just binary search the value that gives us exactly right the number of those subarrays that are correct. Then binary search for one that gives us exactly left minus 1 subarrays with appropriate sum, with smaller sum than that value. And then we just subtract the results. So this is just much more coding. And of course it is faster because we'll essentially be getting again a logarithm of n squared, because that's the number of possibilities. And also if the values were even bigger, and we might have some problems with modulo if the numbers here were bigger, because it might be harder to perform a binary search if the sums were modulo, because now they are not monotonic. But in this case, since the numbers are small, we can do it. We still have that logarithm, but that logarithm is over all the possible values of the sums. But every step only takes linear time, so we get rid of this most important n squared situation that we have here. So that's another approach to solving this problem that's asymptotically faster, but it's much more complicated.